Okay, so like we're just going to do a little bit more stuff related to matchings, and then we're going to move on to another topic. Last time we proved this formula, if I've got it right, about the maximum matching in any graph G. This, as a corollary of this, you get something called one-factor theorem. Which says that, so Tutt's one-factor theorem is about classifying which graphs have a perfect matching. So, but of course you could just, if you know this formula, so this completely determines the matching number, right? So if you plug in, so if it has a perfect matching if and only if the size of the, the biggest matching is the number of vertices over 2, right? Because perfect matching would have n over 2 vertices, or sorry, n over 2 edges if you had n vertices. So if you just plug in like size of v, v of g over 2 into this side, it kind of tells you what would have to happen. So anyway, so Tutt's one-factor theorem says that G has a perfect matching if and only if if I look, the size of the cardinality of S, so S is going to be some set of vertices. So the cardinality of S is bigger than the number of odd components of G minus S for every set of vertices of the graph. Okay. And yeah, if you think about it, that's going to follow from this theorem, because if there was some set S where this number, this odd number of components thing, was bigger than the size of S, that would make this minimum less than the number of vertices, and then like the matching number would be less than the number of vertices over 2. It wouldn't have a perfect matching. And vice versa, if it does have a perfect matching, then this must be bigger than, anyway. So so this just implies that, or this formula implies this theorem. Why do we call it one-factor theorem? I mean, perfect matchings are sometimes called one-factors. So this is just terminology. Okay. So now what I want to do is connect this formula to something related to like linear programming and stuff. So recall that the indicator vector for a matching M is the vector which, I guess we're usually just going to write like 1 subscript M. Okay, and this has like some, anyway, the number of coordinates of this vector, like it has a coordinate for every edge of the graph, where 1M UV is 1 if the edge UV is in the matching and 0 otherwise. Okay. So yeah, I want to make some connection between this formula and somehow linear programming. So therefore it's useful to sort of think of a matching in terms of like some kind of a numerical vector, right? Because that's what shows up in linear programming. So here's a definition. So the matching polytope of a graph G is the convex hull of all indicator functions or indicator vectors of matchings in G. Okay, so you basically take matchings and like kind of take convex combinations of them. So, you know, like I could take one matching times 1/2 plus another matching times 1/2, and that would be part of my matching polytope. This is a polytope, by the way, because we defined a polytope to be a convex combination of finitely many vectors. So yeah, that is what this is. And then like, there's a similar definition, the perfect matching polytope well, it's similar, but you know, for perfect matchings. Okay. So you take convex combinations of indicator vectors of perfect matchings. Of course, your graph just may not have any perfect matchings, in which case your perfect matching polytope would just be the empty set, right? Okay. So so for bipartite graphs, the situation, these polytopes are really nice and really simple. We've already kind of seen this before, and actually, I mean, you're really, where this is proved is assignment 3, question 2. You know, you'll prove that, well, if you do that assignment, that if G is bipartite, then the matching polytope ends up being just the set of all fractional matchings. Okay, a fractional matching, remember, all it means is that for every u, if I take the sum over all u v, well, sum over all v in the neighborhood of u, and all of the entries are non-negative. Right, so this is like what a fractional matching is. And like this kind of magical thing that happens is that these two constraints just completely determine the matching polytope if it's a bipartite graph, right? So this is something we already kind of used to take weighted, you know, maximum weight matching problems in bipartite graphs and say, okay, we can reduce it to a linear program because it's just maximizing some function over these constraints, right? And similarly, for perfect matchings, so if it's a bipartite graph, the perfect matching polytope is just all of the vectors that satisfy where this sum equals 1 for every vertex and everything's non-negative, right? So for perfect matchings, all you do is you add an equals instead of a less than or equal to. Okay, but we saw that is just false for usual graphs because this would be an example of a fractional matching. If I put 1/2 on every edge, this is a fractional matching. So this is a fractional matching that's not in the matching polytope. Okay. So actually, there's something quite related to this Tut-Birch formula that actually allows us in any graph to write down a description of the matching polytope and also the perfect matching polytope. Okay, maybe I'll write it here. So let's talk about perfect matchings first. So I'm not going to prove this, but you are going to have to know how to apply this. So you're going to have to understand the statement, basically, because there's an assignment question on it. So Edmond's perfect matching polytope theorem. So the perfect matching polytope, this is actually quite a nice theorem. Of any graph G is the set, so it's equal to the set of vectors. So again, these vectors are indexed by the edges of the graph such that so we're going to have the same initial constraint that, like, okay, for every, if you're dealing with perfect matchings, like every vertex should be in exactly one matching edge, which corresponds to the linear constraint, the sum over all vertices in the neighborhood of U of XUV equals 1. Okay. But then, yeah, this is not going to be enough because of this bad example over here. So we need another constraint, which says that if I sum over all edges in the graph which are contained, so where both endpoints, so UV, are both in U. So U is going to be a set of vertices that we're going to write at the end. And I take XUV, that has to be at most well, okay, I'm going to write it like this, but the size of U minus 1 over 2 for every odd, every set U in the vertices where the size of U is. And then the third constraint is also like a trivial one, just that all of the entries have to be non-negative. Okay. So this is like the like additional constraint that didn't show up for bipartite graphs. And this has got to be true, right? If I wanted to have a perfect matching, and I've got a set of, let's say, yeah, I've got some set U of 5 vertices. Well, just because of how, I mean, matchings, they always connect to, every edge in the matching involves 2 vertices, right? I mean, I could not have more than two edges of the matching inside of that set, because yeah, then it would hit that thing. It would hit something twice, right? So like basically this like little kind of parity constraint is like the only thing that differs when you go from bipartite graphs to general graphs. Any question about this theorem? And like somehow I'm trying to I'm writing this after writing this Tut-Birch formula, because like there's something about oddness going on here, right? Essentially odd size sets are like some kind of barrier to having a bigger matching, and somehow that comes up here and it comes up in that theorem, right? These odd things.
The second condition is true for all bipartite graphs, so it just counts.
Yeah, it must be. I mean, I don't see it off the top of my head, right? Or somehow these constraints must imply this one for bipartite graphs. Yeah, it's not completely obvious why that. And also like the bipartite, if I kind of take this constraint and the bipartiteness of the graph, it must imply this constraint. But it's not completely clear why that would be the case. Maybe that's a good thing I should add to the assignment in a future year or something. Show that this implies the other thing. Now here's one kind of unfortunate thing about this theorem. Like I would love to say, we love linear programs because that linear programs can be solved in polynomial time, right? This gives you, if I wanted to solve the maximum weight matching problem, these are some linear constraints. And so all I would do is you would say, okay, just maximize the weight function subject to these constraints, right? So this does give you a linear program that can solve maximum weight perfect matchings in a general graph. But like, can you see the problem with what I'm saying here? I mean, you could use this to solve the problem, but it might not be very efficient. So the thing is, I take my graph, right, which has, whatever, n vertices or something. I write down this linear program. Just writing down this linear program is going to take me too long. I mean, I've got exponentially many constraints. Every single subset of vertices, every single odd subset, of which half of them are odd, right, has a constraint corresponding to it. So yeah, this does reduce the problem to a linear program, but the linear program has exponential size. So this doesn't really give an efficient algorithm for matching problems. But there does exist an efficient algorithm. We're just not going to cover it in this course. Okay, so that's the perfect matching polytope theorem. There's also a more general matching polytope theorem. So same kind of setup. You've got any graph, and this time the matching polytope I'll just say is described by the constraints. So we've got the same one as usual. If I pick a vertex, the sum over all the neighbors of x of the variable xuv should be at most 1 for all vertices. Okay. I have messed something up here. So this constraint should have been on this theorem. Yeah, this is not this is not quite going to work for this one, maybe. So okay. So I'm going to write the actual matching polytope theorem, and then we're going to fix that one. Okay. This one should have said, okay, I'm going to need to define some notation for this one, but what this should have said is that so I know I haven't defined this notation. I'm going to do it in a second, but this kind of looks like this symbol is meant to be like a partial derivative kind of symbol, like one of these kind of curly things. Or like a boundary symbol in topology or something. So what this means is this is the set of all edges with one endpoint in U and one outside U. So sorry about that. These things are really like quite similar, but not quite the same. Yeah, greater than or equal to 1. Yeah. This is because we're trying to get a perfect matching, like yeah, this is a bit of a different constraint than the other one, right? So this is saying if I really wanted it to be a perfect matching, if I've got a set of 5 vertices, one of the edges that leaves this set U would have to be in the matching. Like if I want it to be perfect, like one of these things has to be like matched involving something outside. It could be more than one, but it has to be at least one. And then maybe these could be matched up inside the set. Right? And this is just saying like the kind of weight of edges leaving an odd set has to be at least 1. There's got to be at least one matching edge that leaves the set, right? Because it's supposed to be a perfect matching. And this one's just saying what we had before, that like you couldn't have more than, you couldn't have more than 2, if you had a set of size 5, more than 2 edges inside of it. But yeah, this is saying you have to have, to make it perfect, you have to have something matching to the outs, from inside the set to outside, right? So yeah, there's a subtle kind of difference there. So yeah, sorry about that mistake, but is that clear now, or any questions about these things?
Perfect matching has x equal 1.
Yeah. Yeah, because yeah, not perfect. This is saying like if it's any matching, for any vertex, there's at most one edge incident to that vertex. That's what this is corresponding to. And if it's perfect matching, there's exactly one edge incident to each vertex. So if you check, like, for example, an incidence, or sorry, what do I call it? Indicator vector for perfect matching would satisfy these constraints. And an indicator function for a matching that's not necessarily perfect would satisfy these constraints. And what this theorem says is that these constraints completely determine those, the convex combinations of those things. Okay. Any questions about that? Okay, so basically you need to understand what these theorems are saying and be able to use them, but not necessarily have to be able to prove them. Okay. So the next topic is going to be on flows in graphs, or in digraphs, really. Okay, so if you've seen like the max flow min cut theorem, that's what we're going to basically be doing. Or Menger's theorem, they're all, I mean, these things are all kind of the same thing. Okay, so although you might have only seen these things in the context of graphs, so we're going to be dealing with digraphs, so maybe it's a little bit more general. And maybe you've never seen these things at all, which is also fine. So let D be a digraph. Let S and T be vertices of D. And let C be a function on the arcs of the digraph where it maps. So every arc gets mapped to some value between 0 and infinity, so it's like a non-negative function. So by the way, we call CUV, so for some arc UV, the capacity of the arc UV. Okay. And now I want to define a flow. So a flow from S to T with respect to C is a function F on the arcs. So again, I'm gonna map every arc to a non-negative number such that, okay, I need a few conditions. So first of all, the flow on every arc has to be at most the capacity. And okay, have any of you like taken like physics, like with circuits and stuff? Like you have Kirchhoff's current law. Have you heard of that kind of thing? If you have some kind of circuit, like if you've got some amount of flow of electricity going into some kind of junction thing, the amount of flow in should equal the amount of flow out. Otherwise, it's going to get, I guess, really hot or something. I don't know. If you got like electrons like flowing in there like faster than they're flowing out, that's going to be weird. Unless you have some kind of, unless that point is like a battery where it's like a source of electricity or something, then you've got more coming out than coming in. But anyway, so basically we want like Kirchhoff's current law, basically. So you want that for any, so the amount of flow coming into a, So I'm going to use this notation. I'm not sure if I've defined it or not, but this means U is a in neighbor of V. So N minus means like, yeah. So I'm summing over all the U that send an arc into V and taking the flow on the arc UV, and that should equal the amount of flow coming out of V. So it's like the sum over U and N plus of V. f of u v, vu. So this is like the arcs coming out of V. Okay, and this should hold for all V, which is in the vertex set, but not equal to S or T. Okay. The way you should think of this is you've got like some S and some T, right? And like, let's suppose you've got some kind of resource, like, I don't know, oil or something, or water or whatever, like that. You're trying to like send that resource through a network from S to T. So like S has a bunch of like, yeah, that's like the source of all of your water or whatever, and you're sending it through pipes, and you're trying to get as much water to T as possible, right? And so, but at any sort of like, you know, okay, I'm just making things up here, but right, at any sort of like, so maybe each of these arcs is like a water pipe, right? They all have some capacity based on like the thickness of it. And anyway, so if I look at how much flow is going, like, let's say there's 2 units of flow going on this edge, this arc, and 2 on this one. Well, I don't want to have like a surplus of water there, so I need, if the flow coming into that vertex is 4, it needs to be 4 coming out. So it could be like 1 that way and 3 that way, for example. Maybe 3 here and 1 here. And then like you could have, I don't know. Okay, that one's already got 2 coming out. Let's say I give it another 4 coming out this way. Maybe I have to send 6 this way. Right, I'm not really dealing with the capacities here, but let's say that this doesn't violate any capacity thing, right? So yeah, this would be a valid flow because at all the internal vertices, the amount of flow coming in equals the amount of flow going out, right? Is it clear what the what a flow is? Okay. And like I said, we're trying to push as much stuff as we can through this network. So we want to, yeah, we want as much stuff to be flowing from S to T as possible. And if you look at it, like the amount of stuff flowing out of S in this example, right, it would be 8 units of flow. And the amount of stuff going into T is also 8. If you think about it, because of these local constraints that flow in equals flow out on every vertex, you're always going to have that property. The total amount coming out of S should equal the total amount coming into T. And we want to maximize this quantity. So we want to, so like our goal is to maximize the value of the flow, which is just the kind of net amount of flow coming out of S. So it's the sum over all vertices in the out degree of S, f of SV. Now, in this picture, I only had arcs coming out of S. I didn't have any going into S. But obviously, if you had arcs coming into S that had a positive flow, like you want the difference of these two things, right? If I've got 8 coming out of S, but 8 coming into S, then, I mean, really, the net amount coming out of S is 0, right? So you want to maximize the amount leaving S minus the amount coming into S. So this is the value of the flow. That's right, yeah. So this, I kind of scribbled it badly in the bottom corner here, but this only has to hold for all vertices that are not S or T. Yeah. So you can imagine, like, yeah, there's some like surplus of like whatever resource it is here, and we're trying to push it over to T. And so yeah, this doesn't have to have the amount in equals the amount out, because it's like coming from here and it's going over there. Okay. Any questions about this setup? Okay. Right. Okay, so then let me basically tell you the answer to this question, like how much, or I mean, let me write down a theorem that kind of determines the maximum value of a flow. I guess first I need a definition. So an ST cut in D is a set of vertices. So it's a set U of vertices such that S is in U and T is not in U. Okay. And I guess another definition is that if I have a set U, so again, if I write this kind of boundary thing, like this kind of squiggly thing, like a partial derivative symbol with a plus with U, this just means the number of arcs that are pointing out of U, or the set of arcs. Okay, so this is my set U. Maybe I've got, some arcs coming in, some arcs going out. So in this case, I'd say that this, I don't know, we call this like the, out boundary or something. Anyway, so this would equal be of size 3. Yeah.
Do the arcs have to start in U?
They have to start, yeah, in U. Yeah. So something like that, like looks like it's pointing away from U. That's over here. Yeah. No, that doesn't count. So yeah, what I mean is it has one endpoint in U and one endpoint out, and it points out. So I think in this example, it'd be 3 because I don't count the ones coming in. I just count the ones going out. Right. And then we can say the capacity of an ST cut U is the sum overall UV in this boundary thing of U of the capacity of UV. Okay, so yeah, if this had a capacity of 7, that had a capacity of 3 and then 9, I wouldn't actually care about these ones, the ones coming in. All I care about is the ones going out, and I just add up those numbers. So the capacity, so let's say S is inside of here and T is outside. The capacity here would be, I guess, 19 because it's like 9 plus 7 plus 3. Okay. So yeah, I really don't care about the ones going in. I just care about the ones going out. Because, I mean, if you think about it, well, yeah. It's not clear why I'm defining any of this, but this is, this brings me to the kind of key theorem here, which is the max flow min cut theorem. So for any digraph D, where and then ST are vertices of D, and we've got a capacity function on the arcs. The maximum value of a flow from S to T with respect to C is equal to the minimum capacity of an ST cut. Okay. Okay, so it's again one of these theorems where the maximum of one thing is equal to the minimum of another, right? So there's a sort of dual here. Finding the highest value flow is kind of a dual to problem to finding the minimum capacity cut. This also, like, if you think about like NP and co-NP and stuff, this also like relates to that. If I wanted to show that the maximum flow has value at least 100, let's say, just pick a number, whatever, 100, I could produce a flow with that value and just check, and then that can be checked in polynomial time. You just check the flow in equals flow out conditions and check the capacities, and then that certifies that it's a flow of high value at least 100. Sorry. But then if I said, okay, prove that there doesn't exist a flow of value 100, well, you could just find a cut with capacity less than 100, and then you've done it, right? So there's a certificate for a yes instance or a no instance. Maybe one thing to note here is that this the max flow problem really naturally reduces to a linear program. Because you just like take your flow, the value of the flow on every edge and arc, and you just make that a variable. The flow in equals flow out condition is just a constraint. What other constraint? Oh yeah, there's a constraint that the flow value doesn't exceed the capacity on every arc, just a linear constraint. And then, yeah, you just have a very simple linear objective function, which is the flow out of S, and you just maximize it, right? So this definitely can be solved in polynomial time by just reducing it to linear programming. And if you think about, yeah, the number of constraints and variables would not be very large, right?
Constant in the number of edges or arcs.
Yeah, exactly. Yeah, yeah. They're both.
Linear.
Yeah, yes, that's what. Yeah, I know what you mean. Yeah, just yeah, exactly. Linear in the number of arcs, like, and also linear in the number of vertices. Yeah, I guess number of arcs is good. Right. So like, yeah, if you wanted to just solve this with a linear program, you could, but we're going to have like a proper, like, kind of combinatorial algorithm. Also, the linear programming approach would probably like point you towards this max flow min cut theorem. But it would, like, the dual of the linear program would actually, of course, it's going to naturally have like fractional values, right? Whereas this max cut problem gives you a very combinatorial object, like a cut, a vertex cut. So this tells you a little bit more than just taking the dual. Anyway. Okay, so we're going to focus on proving the max flow min cut theorem. Okay. So we're going to build this up from kind of more combinatorial, like, yeah, less kind of fractional versions of this to eventually get this theorem. So we're going to start by proving Menger's theorem. Okay, for this I need a definition. So yeah, we're going to come back to this theorem at the end, basically. Or build it up from other things. Okay. So for two sets, S and T, two vertex sets in a digraph, define an ST vertex cut, okay, which is going to be different than the types of cuts we were talking about before, to be a set C of vertices such that every path from S to T you know, at some point passes through C. Okay. I mean, a sort of picture is, you know, you've got S, you've got T, you've got some set C, and like, yeah, every path that goes from, so this is a digraph, so paths have to follow the directions, right? And there's no way to take a path that like bypasses the set C, right? Now note that like this is like the picture I'm often thinking about, but the set C could contain some elements of S or elements of T. The sets S and T could even be like non-disjoint, right? These are just any two sets, S and T. They could be the same set. I have no idea, but yeah, and yeah, the set C could. So for example, if I let C equals S, that would like that set C would be an ST vertex cut because every path from S to T goes through S because it starts in S, right? Okay. So this is the version of Menger's theorem we're going to prove first. So we'll call this like the vertex version of Menger's theorem. So it says that the maximum number of vertex disjoint paths from S to T is equal to the minimum of the cardinality of C, where C, so yeah, is an ST vertex cut. Okay. How many of you guys are familiar with this, at least in graph theory, maybe not digraphs? Okay. Yeah, this is sometimes phrased in graph theory in terms of like the connectivity of a graph, like, or something like, I don't know. I guess, yeah, it's phrased in different ways. Yeah, there's either, between two vertices, there's either K disjoint paths, vertex disjoint paths, or there's a cut of size K minus 1 that separates those two things. And I guess this is just a bit more general also, that it's dealing with sets of vertices instead of, yeah, just two vertices. Okay. Okay, so let's prove this. One direction is really easy. So if C is an ST vertex cut, well, then you can't have more than the cardinality of C vertex disjoint paths from S to T, right? Because I mean, this is a bottleneck, right? Like it's like, well, actually, like all of these theorems, these max flow, min cut things and stuff, you should think of it as like, you know, we're trying to identify the bottleneck that forbids the existence of some kind of disjoint paths or something. And yeah, if I've got, if let's say the size of C is, you know, 10, and I try to send 11 disjoint paths from S to T, well, all of these paths intersect C. So you can't have 11, I mean, because then there's going to be, by pigeonhole, there's going to be one vertex of C, at least one vertex that's used by two paths. Then they're not vertex disjoint, are they? Right? So by pigeonhole, well, so then there cannot be more than the cardinality of C, disjoint, vertex disjoint, paths from S to T by, you know, pigeonhole. Maybe I should be clear what I mean by vertex disjoint paths, right? I mean, it's a collection of paths that are pairwise vertex disjoint, right? Okay. Is that part clear enough? Okay, so that proves that, yeah, that if I take the minimum cardinality of C, that's an upper bound for the number of disjoint paths. So now we need to prove the opposite direction. So now we prove the other direction. by induction on the number of arcs in the digraph. Okay. So, like, let's let K be the minimum cardinality of an ST vertex cut. So the minimum size of C, where C is an ST vertex cut. Okay, and our goal is to find K disjoint paths from S to T. So when I say, yeah, again, vertex disjoint paths. Okay. Okay. So we're going to start by just trying to use induction somehow. We're just take an edge of this, or an arc of this digraph, throw it away, right? And see if we can find the paths now, right? So, okay. I guess maybe I'm not doing the base case of the induction, but the base case is there are no arcs, and then everything is trivial, right? So we can assume there's some arc somewhere. So let UV be an arc of D. Okay. So if the minimum, so if all ST vertex cuts in the digraph where I take away the edge UV, or the arc UV, have size K, at least K. Well, if that was true, I would just be done by induction, because in the smaller graph, all of the vertex cuts have size at least K, so I can find my K disjoint paths, and then I put the arc UV back, and that arc UV is just irrelevant. It doesn't harm those disjoint paths. So then we would be done by induction. Right, take away the arc, find the paths in the smaller digraph, put the arc back, and there's still paths. So there exists an ST vertex cut, let's say C, in D minus the arc UV of size at most K minus 1. Okay. Everyone following that so far? Okay. So I claim that this, I'm just going to first say that, okay, the size of C has to be exactly K minus 1. And the reason is because if I take C and I add in the vertex U, that would give me an ST vertex cut in the original graph. Because if you think about it, if I take a path from S to T in the original graph, or the original digraph, either it goes through C, either it doesn't use the arc UV, in which case it must go through C, or it uses the arc UV, in which case it uses the vertex U. So the set, if I take C union U, is a vertex cut so I mean an ST vertex cut, right, in the digraph D, right? Because like I said, if you take a path from S to T and D, either it doesn't use this arc, in which case it must go through C, or it uses the arc and then it uses the vertex U. So the size of C union U must be at least K, which implies that the size of C is at least K minus 1. So all I'm saying right now is that this set C has size exactly K minus 1. Okay. Right. So the reason I know this is because in my original digraph, K is the minimum size of an ST vertex cut, right? So, yeah. Okay. Any questions about that?
Why can't we just take the ST vertex cut of size K because we know it exists?
Yeah, that's a good question. I mean,
Means there's some.
yeah, I guess if you, like, you could start with your minimum vertex, ST vertex cut in the original thing, take away an edge, but at that point then, like, you know that there's an ST vertex cut in the new digraph that's smaller, but it may not have anything to do with the first one you found. So like, yeah, so you would just end up probably starting again anyway and coming up with this vertex cut, and yeah, so yeah, you can't really guarantee where it's going to be, but you just know it exists. Okay, so here's like a kind of diagram to show what we're going to do. So suppose I define C sub U to be the set C union U, and C sub V to be the set C union the vertex V. So the idea of the proof now, right, I've got S, I've got C, I've got T, and then I've got the vertices U and V, right? And the set C sub U is what I get by adding U to C. And C sub V is what I get by adding V to C. And I know this arc exists, right? So there's an arc from U to V. So the idea is actually kind of simple at this point. What I want to do is find disjoint paths that go from S to C. Sorry, CU. So if I can, so, and by the way, so CU has size K, right? And C has size K minus 1. I want to find, so our goal is to find K disjoint. So disjoint, I mean vertex disjoint paths from S to CU and CV to T. Right, so the kind of picture is like this. Right? And the idea is that this is going to be a good thing to do because, because, you know, I'm going to take these disjoint paths that go to here. This one, the one that goes to U, I can tack on the edge, the arc UV, and then I can follow along the path over here to T, right? And then all of the other ones, like the ending point of the first path can just be the starting point of, well, yeah, I just continue on from there to t kind of thing. So we have to show that, first of all, that these k disjoint paths exist from u to cu and cv to t. And we have to show then that they, when I kind of glue them together in this way, that they stay vertex disjoint. Okay. But is the diagram clear? Like, I'm going to try to get from S to Cu with k disjoint paths. So it's going to hit every vertex of Cu exactly once, because C has size exactly k minus 1, right? Cu has size k. And then I'm going to follow along, this one I'm going to follow along this edge, and then, anyway, it's going to go over there. Okay. So I guess then the question is, first of all, why are there k disjoint paths from S to Cu? Well, I mean, actually, and I should be more clear what I mean by this. I'm actually going to find these k disjoint paths from S to Cu in D take away the arc UV. So both of these sets of arcs, these sets of paths, I'm going to find in this smaller digraph, because that allows me to use induction, right? I can't use induction in the digraph D, but I can use induction in here, right? And so the reason these paths exist is because either they exist, so by induction either those paths exist, or there's some small vertex cut that forbids them, right? But that would be a set, so okay. So suppose, so either the k disjoint paths from S to Cu exist, or there exists an S Cu vertex cut X in D minus UV, where the size of X is at most k minus 1, right? So by induction, either I find the paths or I don't. Well, or I find a cut. Okay. And yeah, I claim that this would be a contradiction because the set X, so I claim that the set X would be an ST vertex cut in the digraph D, which would be a contradiction, right? Right, because it must be, because every path from S to T goes through Cu. But this is saying every path from S to Cu goes through X. So therefore, every path from S to T must go through X, because it has to get to Cu, and to get to Cu, it has to go through X. So yeah, this would be, if this thing existed, it would be an ST vertex set in the original digraph D. Okay. Anyway, and then similarly, you've got these paths from CV to T. Okay. Now, I guess the key thing we need to notice is that these paths are not going to like kind of intersect each other and stuff. So like, can you see why that's not going to be the case? So anyway, the paths, so these paths won't share internal vertices. So of course, like this path has the same end vertex as the start vertex of the other one, but they won't share any internal vertices. With these ones. Okay. Can anyone see like why that's the case? I'm not even sure if my question's clear or not, but what I'm trying to say is that like you're not going to have this vertex being the same vertex as that one. Like that really this like I won't have this path coming back and using one of those vertices. So I claim that that would be a contradiction if that happened.
Well, then one of those paths could skip over C.
Yeah.
'Cause
Yeah, that's the idea. Like, imagine this was, like, these are actually secretly the same vertex. What you would do is you could take a path, so a path in D, take away UV. So I'm not going to use the arc UV. I could take a walk from, or a path from S to this thing, and then I could just continue over here and go to T. And I would skip the edge UV, and I would also skip C. But C is supposed to be an ST vertex cut in D minus UV, and that would be a contradiction. So, so they won't share any internal vertices with these because C is an ST vertex cut in D minus UV. Okay. Anyway, that supposedly completes the proof. There might be a few details that I've messed up there, but I mean, this is the idea. I'm not sure if I wrote all the details down, but okay. We're close to being able to prove this now. So there's a different version of Menger's theorem. So we did the vertex version. Now we can have like an arc version. So let D be a digraph. And take two vertices ST in the vertex set of D. So this time they're not subsets, they're just vertices. The max number of arc disjoint paths from S to T equals the minimum of, so this quantity, so this is this like kind of outward arc boundary, like of a set U, where U is an ST cut. Okay. So this is actually very similar to the Max-Flow-Min cut theorem, except now we're looking at arc disjoint paths instead of like a flow, right? Okay. And it turns out this follows pretty quickly from the vertex version of Menger's theorem. So apply, so maybe I won't put all the details just so I can get to the proof of the Max-Flow-Min cut theorem, but apply vertex Menger theorem to the arc, line. So like if you've seen like line graphs in graph theory, you can have like a line digraph of a graph. So the vertices of the line digraph are the arcs of D. Okay. And then if I've got, if I've got UV, I've got two arcs, UV and XY. So these two things form an arc of the line digraph if and only if the second vertex of the first arc equals the first of the second. So V is equal to X. Okay. And basically, if you just apply Menger's theorem to that thing, then that'll work. So like the picture for this is like, so these two arcs in D. So each arc is a vertex of the line digraph. So this is a vertex and that's a vertex, and these would be adjacent, or there'd be an arc from this vertex to that vertex, which just means like you're able to follow, like if you take a path, you can take this arc and then that arc next. So there's an arc between two arcs if they could be consecutive arcs on a path. Okay. Okay, let's think about the max flow min cut theorem now. I guess like what if I had a capacity function where I just put capacity 1 on every arc, right? Suppose every arc has a capacity of 1. Oh, yeah, okay, maybe I don't have time for this because, well, okay. So I have to first prove that the max flow is at most the min cut. That's a fairly basic thing. I mean, but yeah, maybe we'll talk about this next time. But basically, like the smallest capacity of a cut gives you a sort of bottleneck where you cannot have a flow higher than that, right? Imagine I've got a set of vertices containing S, and all the arcs coming out of that set have capacity adding up to 10. You're not going to be able to push more than 10 flow out of that set. So therefore, you can't push more than a flow of 10 out of S because there's some set that creates this bottleneck of 10. And basically now if I want to show the max flow is at least, so this is just a rough description, next time we'll do it properly. If I want to show the max flow is at least the min cut, if all the capacities were 1, I would just use the Menger theorem thing, the arc version. I would just say, okay, because now if all the capacities are 1, then the cardinality of the number of arcs leaving this cut is just equal to the capacity, right? Because you just count 1 for every arc leaving. And yeah, so if the minimum cut is at least 10 or something, this arc Menger's theorem says I can find 10 disjoint paths. I just push all the flow along those paths, and that'll give me a flow of 10 going to from S to T. Then you have to build it up like, okay, what if they were integer value capacities? What if they were rational? What if they were real? But each of those things you can just build up kind of one by one. But yeah, we'll do that next time.